In this recording, we will discuss number 3. It says, how many years will it take for an investment of $2,000 to become $8,000 with an interest rate of 4% compounded monthly? So clearly, this is a compounding monthly question, whereby we've got to find the number of years. So we are solving for the number of years. So before we go to the actual solution, let us do a little reading with regards to compounding monthly. So here it says that compounding monthly means that interest is calculated and added to the principal balance 12 times per year, because there are 12 months in a year. So every month end, interest will be added to the principal balance. This can accelerate the growth of an investment or loan compared to less frequent compounding periods, such as annually. So compounding monthly is more advantageous for an investment or loan than compounding annually. The formula used to calculate the future value, A, or the actual value, is A is equal to P times 1 plus R over N in a bracket raised to the power of NT, or raised to the exponent of NT, where P is the principal, that's the initial amount, R is the annual interest rate in decimals, N is the number of times interest is compounded per year, 12 for monthly, and T is the number of years. So for this question, we are solving for T, because it says how many years. Now it continues by telling us how it works. So more frequent calculation. Interest is calculated and added to your principal each month instead of once a year. Interest on interest. Because the interest is added to the principal every month, it starts earning its own interest in the next month. Okay? So you start with a principal amount. Interest is added after a month. Now the interest is calculated on that new value, not the original principal, the new value after the interest was added. The first interest was added, then the second interest is taken on that new greater value, if you want to put it that way. So it starts earning its own interest in next month, leading to faster growth over time. Increased earning returns. This more frequent compounding can lead to higher returns on investments and more interest paid on loans compared to simple interest or less frequent compounding. So this monthly compounding has its advantages over annual compounding. So here we have an example. It says to find the future value of an investment of $5,000 at an 8% annual interest rate compounded monthly for 1 year. So here, this question is not really concerned about calculating the number of years. The number of years is 1. What it wants is the future value, the actual value, the A. So it's a simple case of substituting into the formula. So P is 5,000, that's the initial amount. R is the interest rate, which is 0.08. R must be placed in decimals. N is equal to 12, because N is the number of times compounding takes place, and that is 12 months a year, and the number of years is 1. So the simple case of substituting, and here you can see it says $5,000, open bracket 1 plus 0.08 divided by 12, close bracket raised to the power of, or the exponent of 12 times 1. And 12 times 1 is 1. and 0.08 divided by 12 is 0.006666 continually. And when you add 0.006666, etc. to 1, you get 1.006666. Raise this up to 12, and then you multiply by 5,000 because exponents comes before multiplication. So you must raise up 1.00666666, etc. Raise it up to 12 and then multiply by 5,000 to give you 5,416 and 68 cents. So let's check out our example. But in our example now we have to solve for t. So it says, how many years will it take for an investment of $2,000 to become $8,000 with an interest rate of 4% compounded monthly? So as you can see, P is the initial amount, which is 2,000. A is the actual amount, which is 8,000. As the future amount, N is 12, and R is 0.04. Okay, now we are familiar with the formula. As you can see, here is the compound interest formula. Here is the amount, the actual amount. P is the principal. So P is the principal amount, the initial amount. 1 plus R over N. R is the interest rate in decimals. N is the number of times interest is compounded per year. And the exponent is N times T. T is time in years. So here we substituted in the place of the amount 8,000, and 2,000 is the principal. 1 plus R 0.04 divided by 12. 12 is the number of times compounded per year, which is every month. Raised to the exponent of 12 times t. We don't know what is t, that's what we're solving for. Now we divide by 2,000 to cancel out 2,000 because 2,000 is being multiplied to all of this right here. So 8,000 divided by 2,000 will give us 4. And at the same time now we divide 0.04 by 12 to give us 0.00333 recurring. Now 8,000 divided by 2,000 is 4, and 1 plus 0.003333 is 1.00333. Now t now is part of the exponent. And in order to tackle the exponent when it's unknown, we can use logarithms. Okay, so to cancel out 12t from the exponent, we must apply logarithm, specifically the power rule for logarithms. And here we are going to talk about the power rule for logarithms. So the topic of logarithms, it says here the main rules for logarithms are the product, quotient, and power rules, which allow you to expand or condense logarithmic expressions. Okay, other key rules include the identity rule, etc., the zero rule, and the inverse properties that show logarithm exponentiation are inverse functions. So the inverse of exponentiation is logarithm, and we want to find the inverse of that exponent in order for us to solve for t. T is part of the exponent. Okay, so therefore now we apply the power rule, not the product rule, the power rule. It says the logarithm of a number raised to a power is the power times the logarithm of the number. Okay, so if you have the logarithm in a particular base of a number raised to a power, that is equal to the power times the logarithm in that same base of that number. Okay, so those two are equal. So we can replace this term with that term, where P now is now a product with the logarithm of the number. So here you have an example, logarithm in base 10 of 5 raised to the exponent of 3. Okay, so therefore now This is the same as 3 times the logarithm in that same base times 5. As you can see, the exponent 3 or the power of 3 becomes a multiplication in front of the log. So all we need to do is to take logs on both sides in any particular base. We can use base 10. Okay, so log in base 10. Actually, there's a base 10. It is not written, okay, but it is implied. Okay, so you can look in your calculator and you'll see log. And if you see log by itself, that means there's a base of 10. Okay, if you put the 10, that's okay. If you don't put the 10, is the same thing. So that's logarithm on the left side and logarithm on the right side in base 10. So that will permit us now to take the 12t exponent power, whatever you call it, and bring it to multiply log of 1.0033. And since this is multiplication now, we can divide by log 1.0033 to cancel it out. So divide log 4 by log of 1.003333, etc. And that will be equal to 12t. And then we have to finally divide by 12. So we work this out. We'll call what is log of 4. We're supposed to get 0.602. Check it out. We work out what is log of 1.00333, etc. We're supposed to get 0.001444. And we divide by 12. After we divide those two, we get 418.05. And finally, we have to divide by 12 to find what is t. And t is about 55 years. That's the amount of time, more or less, that it took the investment of $2,000 to reach $8,000. Took about 45 years. Number 4 will be done in a subsequent video.